Our first lecture concerning the cardiovascular system is going to be discussing the different types of cells that are found in the heart and their general behavior, their general physiology, and then also discussing stroke volume and cardiac output. We're going to start off focusing on one particular layer of the heart wall. There's three layers, of course. There's the endocardium, myocardium, and the pericardium, and the visceral and parietal pericardium. We're going to be focusing in on the myocardium, myo, M-Y-O, meaning muscle. That muscle layer indicates that the heart basically is one big muscle, and so that is what we are drawing. Towards the apex of the heart, or kind of the pooching off lower part that we're looking at here, the apex is going to be quite thick. These are the walls that surround the ventricles. And then up towards the top, or the base of the heart, we're going to see thinner walls surrounding the atria. So it indicates that the ventricles are quite thick and muscular, and that's pointing to their role in pumping blood throughout the body. So we have these thick walls here, including the outer walls, and then the interventricular septum as well in the middle there. Let's go ahead and label the myocardium. Most of the cells of myocardium are going to be muscle cells. In fact, 99% of the cells that we find here are going to be contractile cells. They actually have several different names, but for our purpose today, we're going to call them cardiac contractile fibers or cardiac contractile cells. So 99% of the cells that you see there are muscle cells. But additionally, we do have a significant number of specialized cells that have an electrical impulse that they carry. These are called autorhythmic cells, and they basically make up two little beads. We'll be discussing these and naming them in the next lecture, but for now I kind of wanted to draw their presence throughout the heart and just focus in on what they are. These are autorhythmic cells. They have several different names as well, but we're going to call them autorhythmic cells, and this makes up about 1% of your myocardium, these specialized electrically generating cells. And for the sake of kind of having a visual here so we can really understand what's happening, I looked up what the autorhythmic cells actually look like, and they actually have quite a bit of variability and some unusual morphology. So I decided to sketch them sort of like this, sort of these squarish looking cells with the wiggly sides, and pop a nucleus in the center there to indicate that they are in fact cells. And then a little bit more familiar to us, we're going to go ahead and draw some of those cardiac contractile cells as well. When we look at heart tissue, of course, this is what we're usually looking at, these cells with these intercalated discs, these wiggly lines. They're sort of short, rectangular sort of cells. They usually only have one nucleus, but they have these wiggly lines called intercalated discs, which distinguish them from any other cells of the body. Pop some nuclei in there as well. Let's go ahead and investigate those intercalated discs. The intercalated discs are pretty well organized interactions between the cells. And these intercalated discs have a few different proteins there. They have desmosomes to hold them together, but they also have gap junctions. These gap junctions are very significant for what we're discussing today. The gap junctions basically allow a continuous interaction between the cells. It basically makes the cytoplasm continuous from one cell to the next. A gap junction is a pore between the cells, or like a tunnel that goes from one cell to the next. We have to spend some time discussing the electrical impulses that are generated by these autorhythmic cells. It's called a pacemaker potential. And as you see, I drew an arrow that goes basically between the different cells, and then it actually interacts between the cells and then interacts with the neighboring muscle cells as well, the neighboring contractile cells too. The pacemaker potential itself, this electrical impulse, looks somewhat like an action potential that we've seen in the past, with a couple of variations that are extremely significant. The one that I'm labeling right now, this slow sodium influx that goes through sodium leakage channels, is extremely significant. And oftentimes this is actually what is responsible for what we call the pacemaking ability of these cells, the fact that they are continuously drifting upwards, the fact that they are constantly slowly depolarizing because of that slow sodium leak. It happens all the time, And that's actually what allows these to be auto-generating. They're called autorhythmic cells because they themselves are constantly depolarizing. It's hard to overstate the significance of this. It means that a heart does not actually have to have any interaction with the nervous system itself. Those autorhythmic cells are kind of like the heart's own little nervous system inside of there. These are not neurons, at least in my opinion. These are not neurons. There are people who call them neurons, but since they're not actually connected to the nervous system, to the brain or the spinal cord, they're not neurons. They're just electrical cells within the heart itself, autorhythmic cells. So this slow sodium drift upwards, this slow sodium leak, the influx of these positively charged sodium ions allows you to constantly have this depolarizing drift, this upwards drift. I know I keep saying this, but it's so significant and important that the redundancy, I feel, is actually important and merited in this case. This slow sodium drift, this slow depolarization allows these cells to be self-generating, self-depolarizing cells. Once you hit that threshold mark, you then open up voltage-gated channels. In this case, it's going to allow for calcium to flow through the voltage-gated channels and allows calcium to flow in quite quickly, and which allows for an even faster depolarization. And then on the other side, we have a potassium efflux, which is responsible for the repolarizing stage there, which is mostly actually caused by those calcium channels, those voltage-gated calcium channels closing. Now, it's important to recognize that there's actually an electrical impulse that continues to move through the muscle fibers. I'm going to spend a little time talking about this. So yes, we have the autorhythmic cells generating the pacemaker potential, which is an electrical signal that then can be passed on to those muscle fibers. But the muscle fibers themselves, those cardiac contractile cells, also generate an electrical impulse, which also can be passed on. This impulse is called a plateau potential, so named because it has kind of a distinctive flat top, sort of like a plateau in nature, what a plateau looks like. The depolarizing phase in this case is going to be sodium influx. The flat top is going to, and it has a kind of a distinctive point there, which usually is just a little bit of potassium efflux, followed by calcium influx. The calcium influx is what allows this flat top to be flat, and it lengthens this potential. And then, of course, we have a potassium efflux on the other side, causing that repolarization or the downward drift of the signal. I want to spend a moment discussing the different dynamics, similarities and differences between skeletal muscle fibers and cardiac muscle fibers. There's an awful lot that is the same between them with a couple of distinctive features. So on the left-hand side, we're drawing a cardiac fiber. On the right-hand side, we're drawing a skeletal fiber. Of course, one of the things we know about skeletal fibers is that they're quite long and that they have these stripes called striations. The cardiac fiber is quite short, but it also has those striations. Now, the presence of striations indicates quite a lot of information that we're not showing in this video. For example, the idea that there are sarcomeres inside of there. Those stripes are highly organized myosin filaments, and of course, these are the thick filaments. That also implies that there's thin filaments, that there are T-tubules, that there's a sarcoplasmic reticulum. The release of calcium interacts with troponin and swings the tropomyosin blockade out of the way of the actin active sites, and therefore the myosin heads are able to bind and perform excitation contraction coupling and cross-bridge cycling and all the things that go along with there. So there's quite a lot of information not shared here, but the idea is basically that both cardiac muscle fibers and skeletal muscle fibers have very, very similar microphysiology. The way that they contract is just about the same. Now, one of the things that is also similar but has a significant difference here is the way that they interact with an electrical impulse. So, as I said, the skeletal muscle fiber actually is a very long cell, and therefore you're able to extend very fast communication along the length of the sarcolemma, the outside of the cell, that outside membrane of the cell. Now, the cardiac fibers each individually are quite short, but remember about those gap junctions. The cytoplasm from one cell to the next, the inside of the cells are basically continuous. And so it's almost like having a very long cell, just like the skeletal muscle fibers, and therefore they also have very fast communication. So let's go ahead and draw the electrical impulse in purple, which is the driving force of that electrical impulse along the outside of the membrane, the sarcolemma, the plasma membrane of the cell. And in both cases, it just does exactly the same thing. And what I want to say here, in purple, we're going to write the electrical impulse, followed by, in blue, the contraction of the muscle fiber. Sometimes it's not completely clear that happens. Oftentimes we'll discuss for example, the electrical impulse that comes from the motor neuron or from the autorhythmic cell, and then we'll talk about the contraction of the muscle. But in fact, it's important to distinguish, I think, the electrical impulse of the controlling cell, the neuron or the autorhythmic cell, and then also talk about the electrical impulse that is generated along the length of the muscle cell, and then followed by the contraction of that muscle cell, whether it be a cardiac muscle fiber or a skeletal muscle fiber. So now that we've kind of drawn a picture, a sketch that kind of shows how it works at a cellular level, now we want to actually show the trace. We want to show the electrical impulse in an XY axis. On the x-axis, we're going to be drawing time in milliseconds. And on the y-axis, we're going to draw membrane potential and in millivolts. We're actually not going to draw numbers on the y-axis because it can vary quite a bit depending on certain dynamics of the cell and so on. Up above, we're going to be drawing the heart cell, and down below, we'll draw the skeletal muscle fiber. So let's start with the skeletal muscle down below. The first thing we're going to do is make room for about 200 milliseconds. That's about the time course that we'll need for the whole shebang to go forward. We'll start off with drawing a muscle, an action potential of a neuron, and we're going to contrast that right away, that horizontal line with that angular line up above. So the horizontal line there represents resting membrane potential. This is an action potential that is generated by a neuron, a motor neuron in this case. So an action potential of a neuron, it's got the depolarization, the depolarization, the repolarization, the hyperpolarization. We have studied this before. This then is followed by that electrical impulse in purple, remember? The electrical impulse that is generated down the length of the sarcolemma, which is called an excitatory junction potential. And this in turn is followed by, in blue, the actual contraction of the muscle. So the action potential, neuron, excitatory junction potential, the electrical impulse of the muscle, followed by the contraction of the muscle. And you can see the time course there. The action potential itself is on the order of maybe 5 milliseconds start to finish, followed by about a 100 millisecond excitatory junction potential, and that actually, as it's still happening, causes the muscle contraction to occur, which is maybe on the order of 150 milliseconds in total, maybe 100 to 150 milliseconds, kind of depending on where you begin to measure it. We are going to need about 3 times as much time. As you see, it kind of ran out of room here, but we need about 600 milliseconds to allow for all of the activity that's going to be happening, that's going to allow your heart muscle fibers to actually contract. And so although the time course is not perfect here, the basic indication is that we want to give the idea that it's just a much longer time course with cardiac muscle fibers than with skeletal muscle fibers. And in blue, we do have to add one metric here. Rather than measuring this in millivolts, of course, muscle contractions are simply measured by their tension. So we kind of stick that on the other side there. Both the action potential and the excitatory junction potential are measured in millivolts. But the muscle tension is measured in tension. All right, so yeah, I kind of had to squash it in there a little bit. The time course is not perfect here. But basically, we're going to start this one off with the contraction itself, because we do want to indicate that it's a it's even longer than is indicated on this piece of paper. I simply ran out of room. So we have our cardiac muscle contraction, quite profound. It's actually going to be a higher amplitude as well, but we're indicating here the length of the contraction. And that is preceded by a plateau potential. The plateau potential is basically the correlation of the excitatory junction potential. But remember, a difference here is that we have that calcium influx as well. The plateau potential is that electrical impulse in purple, remember, the electrical impulse that is making its way down the length of the sarcolemma surrounding the cardiac muscle fiber. And that in turn, the plateau potential is preceded by that all-important autorhythmic cells pacemaker potential. So the pacemaker potential starts off the whole shebang, and as you can see again, it's similar to an action potential, but a much longer time course, and of course that incredibly important sodium leak that allows that upward drift of depolarization every single time. So again, just to recap, skeletal muscle fibers, we have an action potential by a neuron, followed by an electrical impulse in the muscle cell called an excitatory junction potential, which in turn causes the release of calcium that leads to that skeletal muscle contraction. On the cardiac muscle fiber, a pretty similar story. We start off with a pacemaker potential, followed by a plateau potential, a pacemaker potential of the autorhythmic cell, followed by a plateau potential of the cardiac muscle fiber that runs down the length of the muscle fiber and also extends to all the neighboring cells, of course, and that in turn is followed by the contraction of those cardiac muscle cells. Right, so we're going to start with our second big topic today, which is stroke volume and cardiac output. So stroke volume is measured by EDV minus ESV, EDV meaning end diastolic volume, diastole being the resting phase of the heartbeat, and ESV meaning end systolic volume, systole being the contraction phase of the heartbeat. So let's talk about what that actually means in principle. Now, if end diastolic volume is the volume of blood left in a ventricle after diastole, that means that EDV, end diastolic volume, would be the amount of blood that filled the heart while it rested. Basically, between the squeeze of the heart, between the contractions of the heart, there is a significant period of time when blood is flowing back into the heart from the lungs or from the body, flows through the atria and basically makes its way directly into the ventricles for the most part, and then that's the amount of blood that's left after rest. So EDV, end diastolic volume, is going to be a pretty big number usually in comparison with the rest of the numbers that we're looking at here. And systolic volume is the volume of blood left in the ventricle after it contracts. You want this number to be pretty small because what you want is your stroke volume to be pretty big. Your stroke volume is the amount of blood you are actually able to push out. So picture, if you will, the ventricles, the contractors, the pumps of the heart, squeezing hard to try to get blood to the lungs, to the rest of the body, to the systems of the body, to the tips of the fingers and the tips of the toes. You want that to be a really good squeeze. You want your stroke volume to be a good, healthy number. So you want less blood to be left behind after the squeeze. So your ESV, you actually want it to be low. That's a healthy situation. If your ESV is low, that means that you were able to pump quite a bit of blood out with the heartbeat, with the contraction of the heart. So typically our hypothetical numbers would be an EDV of 120 milliliters per beat. Our ESV would be about 50 milliliters per beat, and therefore our stroke volume would just be subtracting the two numbers, and we come to 70 milliliters per beat. So this is a typical stroke volume, 70 milliliters per beat. And keep in mind what that is. The stroke volume is the amount of blood that was able to be pumped out during the heartbeat. 70 milliliters per beat was squeezed out. All right, so then we turn to our next number, which is actually kind of the more important one, which is our cardiac output. Our cardiac output is the amount of blood that is squeezed out of the heart per minute. And the way that we calculate our cardiac output is we take our stroke volume, which we just indicated, and we multiply it by our heart rate. A typical heart rate is going to be about 70 beats per minute. And so we're going to go ahead and set this up so that we're clearly placing numbers in the numerator and the denominator. So 70 milliliters per beat, milliliters in the numerator and beat in the denominator. That's our stroke volume. And then our heart rate, 70 beats per minute, and beats in the numerator and minute in the denominator. We're going to go ahead and we're going to cancel beats because it appears once the numerator and once the denominator, and we're left with milliliters in the numerator, minutes in the denominator, and then we just multiply 70 by 70 and we come to 4,900. So 4,900 milliliters per minute is our cardiac output, the multiplication of stroke volume times heart rate. Now this is a pretty typical cardiac output. Typical cardiac output, I'm just going to put a box around this, is going to be 5 liters per minute. This number, I know there's a lot of information here, but you must remember this number. You must remember 5 liters per minute. It's going to come up several more times this semester. Your cardiac output is 5 liters per minute. Basically, the volume of blood in your body at rest is going to be going to go through your heart once per minute. 5 liters of blood in your body on average. 5 liters per minute goes through, and even more, by the way, when you're exercising. So at rest, 5 liters per minute, the volume of your blood moves through your heart basically once per minute. Now there are various things that can change the way that your cardiac output occurs, or that your stroke volume occurs, for example. And these 3 things we're going to go ahead and write over here, and we're going to draw little sketches to indicate each of them. Preload, contractility, and afterload. It's easiest to start with contractility because contractility is a pretty easy concept. It's basically the ability of your heart to contract, contractility. So we're going to not even draw in the chambers or anything, just the outline of a heart, and we're going to draw some arrows indicating the squeeze inward of all of those walls of the heart. And we're going to draw the clue down below that this is strength. Like the key word here is strength. The strength of contraction makes quite a difference. If you have nice, healthy myocardium, then the strength of your contraction, your contractility will be higher. However, if you are suffering under conditions, for example, of congestive heart failure, the strength of your contractions might be much lower if you are suffering some damage to your myocardium, for example. All right, and then our next indication is afterload. Our afterload is going to be a condition where this is basically a measure of blood pressure. The one chamber of the heart we're going to draw in this case is actually going to be your left ventricle, the most important chamber of your heart. And we're going to go ahead and draw our aortic semilunar valve and our aorta. Kind of a skinny aorta there, but it's this big old tube that leaves out of the heart and brings blood to the rest of the body. It's incredibly important. The left ventricle is the chamber that actually pumps that blood. So there's always kind of like an interplay between the aorta and the left ventricle. The left ventricle is trying to pump the blood out, and then there's always some level of pressure inside of the aorta. It's what we call blood pressure. So our key word is blood pressure, and so that pushback there indicates how hard the heart has to work, basically how hard the left ventricle has to work to pump blood against that pressure. So afterload, blood pressure, and the chamber that we're most interested in is the left ventricle, and the artery we're most interested in for this is going to be your aorta. The last of the variables we're going to discuss is preload, and the preload is basically the filling of the heart. While the heart is resting, during diastole, of course, during diastole and the resting phase of the heartbeat, we're going to have preload, which is basically how much can your ventricles fill up. So we're going to draw little arrows indicating that we're going to be bringing blood back through the atria, left and right atria, and back into the ventricles, left and right ventricles. And so this is the filling of the heart during the resting phase. So preload, contractility, and afterload. What you want to think about is you want to think about how these would change things like EDV, ESV, and then change the number of stroke volume, and then in turn change the number of the cardiac output. And if the number indicates that the cardiac output is a little higher under those conditions or a little lower under those conditions, then you have to adjust your heart rate in order to deal with that. So for example, if we had an individual who had really good contractility, let us say that this was a high top athlete, really healthy heart, and their contractility was excellent. Their myocardium was completely undamaged, and it was very used to pumping lots of blood to the body, and so it was quite healthy. And so in that case, you might indicate, well, the contractility is so strong that actually the stroke volume is super, super high. And after the contraction, there's very little blood left behind. That is going to be changing then the ESV, the end systolic volume. Remember, ESV and systolic volume is the amount of blood that is left behind in the heart after contraction. So if the contraction is nice and strong, the contractility is good, then that would indicate that your ESV is going to be low. And that would then change, in turn, your stroke volume. If you pretended that your EDV, which was about the same, which it might or might not be, but let's just keep the EDV at 120. Let's knock our ESV down to 40. What happens to the stroke volume? The stroke volume actually goes up to 80, and then you should go ahead and calculate that out as far as what happens then to the cardiac output and how would your heart rate have to adjust in order to change what happened to your cardiac output. Remember, you only need 5,000 milliliters per minute or 5 liters per minute on average or so. And so those numbers would all be adjusted in keeping with that.